Okay, welcome to Stat 479, Multivariate Statistics, Lecture 9. So today we're in the middle of our discussion on generalized linear models, and so today's the focus is going to be on algorithms in particular. How do we actually find the maximum likelihood estimates for generalized linear models? And in particular, I'll talk today about two algorithms that are used or widely used: the gradient descent algorithm. And another algorithm, another interesting iterative algorithm, which is iterative reweighted least squares, and I'll use the acronym IRLS. So I'll talk about both of those algorithms today. So just to kind of recap the framework, just to kind of know the situation that we're dealing with and what we've been dealing with for the last 2 or 3 lectures. So we're again in this supervised setting where you have p covariates and a response and n samples of these. So there's 2 ways to express that data. You can think of it as there's the subscript j for the covariate and a superscript I for the sample index. It's convenient to use this vector notation where xi here is actually a vector, a p-dimensional vector, it representing each covariate, and then yi is a scalar. And so you have n xi vectors, p-dimensional vectors, and then y is a scalar. That's going to be convenient notation to use when we talk about the generalized linear model. And importantly, we're kind of thinking about yi could be any general data type. So it could be binary, it could be count, it could be continuous, and the generalized linear model framework will help us kind of deal with all of these different data types. So the model, a statistical model that we're dealing with here is the generalized linear model. And so what that means and what we've kind of gone through in the last lecture or two is what does this model actually mean? And so what it means is that the yi has this distribution p, and then it's related to the covariates through xi transpose b. So b are the parameters of interest. Again, that's a p-dimensional vector that kind of represents like the linear coefficient of the objective, and then p follows a natural parameter exponential family, which is what has been kind of the main focus of the last couple of lectures. And so in particular, to write out the form, so the natural parameter exponential family has this form where theta is the natural parameter, a is the log partition function, and h is kind of this the space measure. So what we're really saying is that xi and yi, they're independent, and also that we have that the distribution kind of follows this form of relating xi and yi when we plug into the natural parameter exponential family. So in the previous lecture, we talked about maximum likelihood estimation. So a natural choice for estimation when you know the distribution is maximum likelihood estimation. And so since so what I've written out here is this is the negative log likelihood. Negative log likelihood. This is the maximum likelihood estimator is the minimizer of this objective function. And the nice thing that we have here is that since A is strictly convex and differentiable, beta hat ML is kind of the minimizer of a convex optimization problem. So we'll talk about ways to solve that today. And so that's going to be really the focus of today, ways to actually find that minimizer. And we know that it's the solution to a maximum likelihood estimate. But the other thing that we'll recall is that since this objective is non-linear, since you can actually solve this by setting the gradient to 0, but you get a set of non-linear equations, and so we need an algorithm to actually solve it because you can't really figure that out in closed form. Okay, so just to we're gonna be concrete. So for example, if we have p is like normal, we'll say theta 1 is our distribution, then our a function is we'll say a of theta is half of theta squared. And what you end up with in that case is that So we'll use this notation. So if we use this notation, that f of b, which is the function that we're trying to minimize today, the negative log likelihood, okay. If this is our f of b, then if a of theta is half theta squared, then f ends up being quadratic. Which is easy to solve. We've already done this. This is where we get the normal equations and then talk about how to find solutions of the normal equations. And this is easy to solve, and we can actually get closed form solutions in that case. But if we have, for example, a of theta equals log of 1 plus e to the theta, which corresponds to p being Bernoulli, where this probability was 1 over 1 plus e to the negative theta, then the objective that we get here is and this is actually, you may have heard the term logistic regression. This is just the logistic regression objective. Okay, and so solution satisfies nonlinear equations. So with no closed form. Okay, and then the other example that we've seen quite a bit is for a of theta equals e to the theta, and that corresponds to p being the Poisson distribution, with the lambda value being e to the theta, and so the objective function, which is the negative log likelihood that we have in this case, is just and this is referred to as Poisson regression objective. For obvious reasons, because because we're starting with a Poisson distribution, and again we get no closed form. So our goal is that for general A, we know that A is strictly convex and differentiable to find okay, so Okay, so let's there's various ways that we could try to solve this, but as I mentioned, one very general approach that is used a lot in statistics and machine learning, and generally tends to work really well, provided you use kind of good step sizes and good starting points, is gradient descent. So so the gradient descent update. Remember that for general f is, or when I say general, I mean it has to be differentiable because we're taking derivatives. And here, and the key question that we need to determine is so we have this sequence of step sizes we need to determine and initial point. So we did this for the case where a is the quadratic. We did that where we were trying to find the solutions to the normal equations, and we found that in that case we got that the starting point didn't actually really matter as long as we chose the step size to be kind of sufficiently small. And so we're going to kind of expect that something like that is hopefully going to occur again. Is something that we're going to need again in this case. And so we're gonna kind of try to develop some ideas which will give us a sense of how to choose these step sizes, and that's going to be really useful in your homework as well, because you'll be implementing gradient descent for these objectives. And one of the tasks will be determining good choices of step sizes. Okay, so since this is the function, the gradient, what does that look like? So we can use the chain rule here to calculate the gradient. You expect this to be a p-dimensional vector because you're taking f is a function of p variables. So when you take the gradient, it should be p-dimensional, and indeed that's the case because the xi's get pulled out, and then when you use the chain rule, you're just going to get the derivative of a prime xit, and then you're just going to get that this is just minus yi because the xi gets pulled out of both terms, and the b, when you've got a linear objective, that linear term just disappears. So this gradient kind of has this form, and so therefore the gradient descent update in that case is okay. Okay, so this is what we get for the gradient descent update. And so then the question is, So how do we choose step sizes? In this case, our analysis is more challenging since a prime is in general non-linear. So updates are non-linear. Okay, and so yeah, this is this makes like kind of deriving like the update equations like we did in the case where a prime was linear when we had f being a quadratic objective. That was relatively straightforward compared to this because here we have a prime, and we know that a prime is we know that a is a strictly convex function, which means a prime has to be a strictly increasing function. But we don't really know too much more about it than that. Okay, and so this is where we're going to use a pretty useful tool, which is we're going to use Taylor approximation. And you can also think of this as like, this is related to the mean value theorem. If this is kind of a bit, something you haven't thought about for a while, that's okay. I'm just kind of the main thing to get out of this whole analysis that I'm doing here is just an idea of how to choose the step size. So the whole point of doing this analysis is it gives you a bit of a sense of how to choose step sizes. Okay, so use the Taylor approximation we're going to try to approximate a prime of xi transpose bt by a linear objective. So what do we mean by that? So we can say that a prime of theta t, so remember that a is a one-dimensional function, so a prime, like the derivative, is also going to be one-dimensional. So what we're going to do is say that a prime of theta t, when we do the Taylor approximation or apply the mean value theorem, we're going to have to do that around a certain point. And so it turns out that the best point to choose to do this analysis is if we let that be theta hat ml. So what that... so I'll explain that notation shortly. Or we'll say theta hat, we'll make this for each I. So we're going to use this notation here because we have to do this one I at a time, so for each sample. And then by the Taylor approximation, so I'm going to explain this notation shortly. So this is going to be theta ti minus theta hat mli. And that's going to be multiplied by the double derivative now because we're doing a first order expansion. So when you take the derivative of a prime, you're going to get a double prime. And then we're going to get this term gamma t of I, where we know that gamma t of I lies somewhere between theta t of I and theta ml of I. So it's going to lie somewhere in these points. Okay, so what does this notation mean here? So theta t of I here is just going to be your xi transpose bt, and your theta hat ml of I is just going to be xi transpose b hat ml. And we'll see why choosing the point that you expand around to be b hat ml is going to be really crucial here. Okay, so what that means is that we have that if we use this approximation and plug in, so recall that we have that b t plus 1 equals Okay, so then what we can do is we can actually expand this out. We'll see that this expansion will kind of lead to some nice things shortly. This is going to be equal to A prime of B xi transpose B to T. Okay, so we're not going to really worry too much about what this gamma t is here. It's just some number between theta ti and theta hat mli. We're going to see later that we're going to, in some sense, say that it doesn't really matter what that is as long as it falls within a certain range. Okay, and so when we expand that out, it's going to begin by looking more complicated, but then we'll see that we'll get some nice cancellations. Okay, so this is what we get as our update, and then let's look at this term here. Okay, so that term is. It turns out that this is actually 0, and why is it 0? Remember that we know that the gradient f of beta hat ml is equal to 0, right? So what that kind of means is that remember that this is exactly what the gradient is. Okay, and so what that means is that your update now kind of looks a lot simpler, and we're going to use some notation to make it look even more similar to what we saw in the Okay, so now we've got, sorry, there's a BT here, I'm sorry. Okay, or let me write it out. it's always important to check that the dimensions match up when you're doing these kinds of analyses. And that's indeed the case. Xi is p-dimensional, and so when you multiply this out, you're going to get exactly a p-dimensional vector. So now we're going to let WT, it's going to be a n by n diagonal matrix. It's a this is something that might look a little bit familiar to you. If you looked at from homework 1, where you would have seen kind of this idea of weighted least squares, and this is going to be a kind of a theme that we're going to see today, where we're going to see weighted least squares, but the weights are going to be different every iteration. You can see there's a WT here. So we're saying WT is a diagonal matrix, so it only has diagonal entries, where WT, we'll use this notation I, because it's, or let me just say, cool. WT, the ith entry, because it's diagonal, is just, okay. So using this notation, you can actually write this out as okay, so remember that X here, so this is a notation that we've already seen here, where X is now an n by p matrix. We put all our data together. R n by n. Sorry, did I miss something here? I think I did, yeah. So this should in fact be, I'm sorry, let me go back here. I made a mistake way back here. This should be a, yeah, in a classroom, someone would have pointed this out. But there should be a beta hat ml here, and that should be times, and so this should be a beta hat minus beta hat ml. Okay, and so we're going to get that this is the same as, okay, so this looks a fair bit more like what we saw in the case of linear updates, but now we have this weight which corresponds to the like this weight which can vary with t. So Okay, so this looks a fair bit more like what we saw in the linear case. Note that if a of theta equals half theta squared, then a prime prime of theta is just 1, and that would just mean that WT is just the identity matrix, which is and this leads to ordinary least squares update. So in the special case where things are normal and we use the ordinary least squares approach, you get exactly the the gradient descent update for you get the gradient descent update that we got previously. Here, the gradient descent update we get has this weight now that depends on t. So again, if you went through the first homework, one of the challenging things there was that you had heteroscedastic normal noise, which meant that you had to have this W matrix in there somewhere to ensure that you were doing some weighting. And so once again, you need to ensure convergence. So what we need is we again need that we need that the sum of the step sizes goes to infinity, as we did for OLS case. But what we also need is we need now that we need this to be this kind of inner matrix to kind of guarantee that that we have a contractive situation. We need this to be between 0 and the identity. Okay, and so one thing I should just mention here is that when you actually implement this algorithm, you're not like computing these WTs or anything like that, because you can't. You don't really know what they are. The point of these WTs is just to do an analysis, which we're doing right now, to help you determine how you would choose the step size. So here we're just finding a way to help us choose the step size. And so how do we know? The first thing to address is how do we know that alpha t x transpose wtx is bigger than or equal to 0? And this is where convexity is really important. We know that since A is convex, and that means that A prime prime of gamma ti is greater than 0 for all choices, for all gamma ti. Like, it doesn't matter what you choose, because it's convex. We have this, or because it's strictly convex. Then that means that for any gamma ti, and so therefore this is why strict convexity is really important here. Because if we don't have that, we couldn't guarantee that things are bigger than 0, and you don't really know what this algorithm is going to do then. Because when it was the identity, obviously we knew that was a positive semi-definite matrix like x transpose x. Now we kind of need the fact that that's bigger than 0 to ensure that we can represent this as a positive semi-definite matrix. And then we also need, as we did before, we need alpha t to be less than the 1 over the maximum eigenvalue of and one kind of approximation you can, or one bound you can use for that is one, like if the maximum eigenvalue of x transpose x times the maximum of I of a prime prime sorry, I'm stuck. Okay, this is going to be the okay, and this follows since that equals to WT I. So you can, I've kind of gone through a few steps of like matrix algebra very quickly here. But the main thing to take out of it is this looks exactly like what we saw in the linear objective, but we have, or when we had this quadratic objective where the updates were linear, except now we have this additional term which relates to the double derivative of a. So we need alpha t is between 0 and and so we need to ensure that and so this actually we need to ensure that this double derivative of a, the strictly convex function, does not get too close to 0 for any iteration. And so just to take a and this actually relates to does not get too close to 0. I should also say this also relates to the choice of B0, which is a starting point. So the general idea is that you want to choose B0 such that A prime prime of B0, or I should say of xi transpose B0 is not too big or small, too big or small. So let's take a concrete example. So if a of theta is e to the theta, we know that that function kind of looks like, sort of looks like this. So so we know that a prime prime of theta equals e to the theta. So want to ensure we want to ensure that theta not too close to negative infinity or infinity, because at infinity the gradient blows up to infinity, and at 0 the gradient gets kind of small, and so therefore what we ideally kind of want to choose is that if I choose theta close to 0. And so the way I would recommend doing that in this case, and what might be useful in your homework, is that if we choose B0 equal to 0, then that means that xi transpose 0 is B0 is 0, and then you can choose that alpha t has to be less than 1 over and then maybe set the and so you could kind of set that maximum to be like, I don't know, set to be, maybe 5 or 10 to be safe. And again, these are just rules of thumb. When you run your algorithm, you'll kind of get a sense of whether your step size is being chosen too big or not. And and as I said before, generally constant step sizes work quite well. Okay, so GD works reasonably well, but one annoying aspect of GD is always having to choose step sizes. Okay, and so the question is, can we come up with an algorithm that doesn't involve such choices? And so I'm gonna just very brief, I'm not gonna have time to do a convergence analysis, and think we've kind of seen enough convergence analyses for the day. But I'm gonna present an algorithm that is actually very widely used for this problem and many others, which is the IRLS, which is iterative. It's another iterative algorithm. Okay, and so the idea actually, you can also think of it as relating to what you did in homework 1, where you had to solve the weighted least squares when you had heteroscedastic noise. So remember, the variance term was different, which kind of meant that you couldn't the maximum likelihood wasn't exactly least squares, because you kind of had to do a weighting. Here we're doing a weighting, but we're doing a weighting at each iteration. So the idea is to solve a quadratic at each step. each step. But we're going to use a different weighting. And so what the IRLS update is as follows. So again, with all iterative algorithms, we need a starting point. So we need a starting point B0 here, okay? And so what the IRLS update is it's just going to solve a different quadratic at each step. So, and I'll talk about the idea behind it. It has quite a nice intuitive idea as well, and I'll talk about that. Okay, so one thing to keep in mind here is this B here is in a function of BT, so it's a function of the previous update. And then we're going to solve a quadratic that uses that as a weight. So what this kind of is, and this is again relates to that first homework, is that remember that expectation of yi is xi is sorry. Because we're dealing with exponential families here, this is just a prime of xi transpose b, okay? And the weight that we use here is actually 1 over sigma hat squared of bt. So this is like 1 over the variance of 1 over the kind of estimated variance. That's why I've used the term sigma hat squared. And so it's 1 over 8. We know that the variance for this this exponential is a prime prime of xi transpose bt. Okay, so remember it's kind of like, you can think about it as so sigma hat squared is estimated variance at b equals bt. Okay, and so another way to interpret this is just that it's the okay, so we, sorry, that's not a BT. Okay, so remember that mu I of B here is just a prime of xi transpose B. So this is something that you actually kind of did in the first homework, but remember that in that case you're dealing with normal random variables with heteroscedastic noise. So your sigma hat squared was just a constant, so you didn't have to do this iteratively, or you just had to do weighted least squares once. Here we're doing it iteratively because the variance is going to change at each step depending on what the BT is. Okay. So this is kind of a nice way to interpret this. So basically each step involves solving a weighted least squares problem. Which is something that you did on the first homework, where the weight, which here is 1 over sigma hat squared of bt, that depends on t. So this should be I should write this as sigma hat I here. Okay. All right, and so therefore we can see that each update will basically satisfy that, if we let, we're again going to introduce a WT notation, which is just, it's a different, I'll use a different notation here. Let's maybe use VT for variance. We're going to let this be in n by n matrix. And it's also going to be diagonal. So at each step, we're again kind of solving a quadratic. So, and we know that VTII is just sigma hat squared I of BT, which is just A prime prime of XI transpose BT. Okay, so what we have then is that BT plus 1 equals argmin of B, and then you can write this again in vector matrix notation as Y equals this is just going to be Y, we're going to say mu of B transpose VT, or VT inverse of Y minus mu of B. And so remember here that Y is in R to the N, where, yi is just y of I, and then this mu b is just in terms of the mean. This is just this is just going to be equal to mu b of I is just going to be A of xi transpose B. Okay, and so this leads to, closed form. I'm not going to go into the details, but doing a change of variable allows you to find a closed form for BT plus 1 at each iteration. And under mild conditions, or we can say that in general, this algorithm converges. So one thing to note is no need to choose step sizes. only need to choose B0 to initialize the variance weights, and then you can use the same choice as you would for gradient descent. Okay, so this is kind of another algorithm, and it turns out that there's this R function which you're going to use on your homework, which is this GLM function. Okay, so if you've installed R, if you look at GLM, that's a very widely used function for this, and you can apply that to logistic regression, Poisson regression, normal regression, and many other kinds of regression. So the GLM function uses IRLS. So this is kind of another iterative algorithm that gives you what you're looking for. So just in summary, two algorithms for finding beta hat ML. One thing I should point out, I haven't gone into the details too much here, is that what I've talked about here is just finding any local minimizer. It turns out that any local minimizer is also a global minimizer because the objective's convex. But it's only as possible at times that you may get more than one solution here, but all of the solutions are equally valid and are all minimizers or maximizers of the likelihood. So, there's gradient descent, and for gradient descent, you need to choose starting point and step sizes. And then there's iterative reweighted least squares, which you only need to choose starting points. Okay, so, and in the next lecture, we're going to actually wrap up this discussion on generalized linear models. And we're just going to spend a brief amount of time talking about 4, which is the statistical analysis. Which kind of addresses this question of, how close is beta hat ML to true parameter B, because we want B hat ML to be kind of close to B. I mean, that's kind of the main idea, and there's various metrics we can use for that. And we're going to kind of discuss that in the next lecture. So that'll kind of round off all 4 components of the framework. We've talked about component 3 for the last couple of lectures, which is the objective and algorithms to find to solve for that objective. And now we're going to say how close is the solution, how close is how close is the outcome of these algorithms to the underlying parameter of interest. And so that'll be the focus of the next lecture. Okay, thanks very much. That'll be all for today.